Hello friends, today we are going to discuss the topic hybridization and shape of covalent compounds for FYBSc chemistry students. Myself Mr. Ramdas Suralkar, Assistant Professor, Department of Chemistry, Pratap College Amarner and Autonomous Institute. What are the content of this topic? We will see the definition of hybridization, what is the need of hybridization, steps involved in hybridization, and what are the characteristics of hybridization. There are different types of hybridization. We can see sp, sp2, sp3, sp3d, sp3d2 hybridization and dsp2 hybridization. We will see then the examples of some molecules like PCl5, SF6, IF7 and NiCN4 2- complex. So what is the definition of hybridization? So hybridization, it is a process of mixing and recasting of atomic orbitals of an atom to form new hybrid orbitals of equivalent energy and shape. For example, sp3d hybridization. So in sp3d hybridization, mixing of 1s, 3p and 1d orbital to form 5 sp3d hybrid orbitals which are of equal energy and shape. What is the need of hybridization? So VBT alone explains only simple linear diatomic molecules like H2, but it is not possible for to determine the correct geometry and correct valency of an polyatomic molecules. So we need hybridization concept. So to determine the correct geometry and bond angle in polyatomic molecules, we need hybridization concept. Also, to determine the correct valency of an atom, we need hybridization concept. In case of hybridized orbitals, the increase in stability due to the lower energy of the hybrid orbital than the unhybridized orbital. So the molecule form is stable compound will be formed with correct geometry and valency with correct bond angle. What are the steps involved in hybridization? There are basically 4 steps involved in hybridization. First, to draw the structure and note the bond angles, that is predict the geometry of the molecule. They decide the hybridization of the central atom from the electronic configuration. From its valence electronic configuration, we have to decide hybridization of the central atom. Then depends on the number of valence electrons and present in the central atom, valence shell of the central atom, we have to determine the geometry of the molecule. So hybrid orbitals move far apart to minimize the repulsion and maximize the distance between them. Fourth step is the bonding. So the hybridized orbital formed by the central atom, they overlap with the p or d orbitals of the surrounding atomic orbital so that it can form sigma bonds with lower energy and more stability. What are the characteristics of hybridization? So number of hybrid orbitals is equals to the number of atomic orbital mixing. So number of hybrid orbital form depends on number of atomic orbital involved in the case of hybridization concept. Hybrid orbitals form stronger, more stable bonds than the pure orbitals. We have seen before that SS overlap or PP overlap, the bonds form are somewhat weakened, while in case of hybrid orbitals, the bond form are very strong and more stable bonds are formed because of the maximum overlap of the atomic hybridized orbital than the pure atomic orbitals. Hybridization involves orbitals of comparable energy only. Means only the if we hybridize third energy level, then 3s, 3p and 3d are only able to hybridize, having comparable energies only. 2s cannot be hybridized with 3s or 3p orbital, that is they must have comparable energy. Hybridizing orbital must have comparable energy. And the fourth point is hybrid orbitals have greater overlapping capacity than the pure orbitals. So their overlapping capacity is higher, therefore the most stable compounds are formed with less repulsion and maximum distance between the orbitals. So they have stable compound with fixed geometry. What are the types of hybridization? There are different types of hybridization. If S and P orbitals are involved in hybridization, then it is called sp hybridization. The molecule geometry of that molecule will be linear. For example, beryllium fluoride BeF2 molecule. sp2 hybridization, the geometry formed by that hybridization is trigonal planar, in which three hybrid orbitals which are formed, which occupy the trigonal corner of the trigonal planar triangle, and they are 120 apart from one another. For example, BF3 molecule, SnCl2 molecule, they have sp2 hybridization. sp3 hybridization, in case of sp3 hybridization, geometry formed by the molecule is tetrahedral. For example, CH4 methane, ammonia NH3, and water H2O, they which involves sp3 hybridization. In case of sp3d hybridization, trigonal bipyramidal geometry is formed. The 5 orbitals are involved, therefore 3 orbitals occupy trigonal planar space, and the 2 hybrid orbital occupy axial positions. So the geometry will be trigonal bipyramidal. For example, PCl5, SF4, ClF3, and xenon fluoride. In case of sp3d2, 6 hybrid orbitals are involved, therefore the hybridization of the molecule will be octahedral, and the example of this hybridization are SF6, BRF5, xenon F4, IF5. In case of dsp2 hybridization, the square planar geometry is obtained. For example, nickel CN/4 2- complex, ICl4-. Example of sp3d hybridization, we will take the example of PCl5. In case of PCl5, phosphorus atom is the central atom, so its valence electronic configuration is 3s2 3p3. There are 5 electrons in the valence shell. In the excited state, this electron gives 5 unpaired electrons, 1 in s orbital, 3 in p orbital, and 1 in d orbital. So one of the paired electron in the s orbital gets shifted to higher energy orbital, that is 3d orbital. So we get 5 unpaired electrons with 5 orbital, and the resultant hybridization is sp3d hybridization. So 5 equivalent sp3d hybrid orbitals are formed, and the geometry of this molecule will be trigonal bipyramidal with 3 equatorial and 2 axial bonds. So structure and bonding of this PCl5 molecule. So 5 phosphorus chlorine sigma bonds are formed due to the result of overlapping of sp3d on the phosphorus atom with 3p orbital on the chlorine atom. So bond angles between equatorial are 120 degree, and between axial are 90 degree, and between axial are 180. So we can observe this structure, that is trigonal bipyramidal, in which 3 hybrid orbitals directed toward the 3 corner of the trigonal plane, and the 2 axial orbitals which are perpendicular to this trigonal planar geometry. So it is called as trigonal bipyramidal geometry because it can form 2 pyramids, one upper pyramid and one lower pyramid. So this is called as trigonal bipyramidal geometry. Another hybridization is sp3d2 hybridization, and the example of this hybridization is SF6 molecule. So sulfur is the central atom, and it is surrounded by 6 fluorine atoms, so it can form 6 bonds. So sulfur belongs to group 16 element having valence shell electronic configuration 3s2 3p4. In the excited state, this electron get excited to higher energy orbital, that is 3d orbital. So we get 1 s orbital, 3p orbital, and 2 d orbital. So sp3d2 hybrid orbitals are formed. These 6 hybrid orbitals directed toward the 6 as per the octahedral geometry. 6 sp3d2 hybrid orbitals, each bond with fluorine 2p orbitals. So geometry of this molecule is regular octahedral with all SF bond angles are 90 degree. We can see the structure of this octahedral geometry, that is 4 atoms or 4 bonds or 4 hybrid orbital directed toward the square planar corner of the square planar, and 2 hybrid orbital which are axial, they are perpendicular to this plane, one is above and one is below the plane. So there are 90, all the angles are 90 in this structure octahedral geometry. Another example is sp3d3 hybridization, that is IF7 molecule. So iodine is the central atom surrounded by 7 fluorine atoms. Both atoms are belongs to halogen family having 7 electrons in their valence shell. So in the ground state, electronic configuration is 5s2, 5p, 5. When excitation occurs, the electrons get shifted to higher energy orbital, 5d orbitals. So the electronic configuration in the excited state will be 5s1, 5p3, 5d3. So resultant hybridization will be sp3d3. So there are 7 hybrid orbitals are involved in this hybridization. Hence 7 iodine fluorine sigma bonds are formed as a result of sp3d3 overlapping with p orbitals of fluorine atoms. So geometry of this 7 hybrid orbital will be pentagonal bipyramid, in which 5 hybrid orbital directed toward the 5 corner of the pentagon, and the 2 axial orbitals, they are axially directed, which are perpendicular to this pentagonal geometry. So pentagonal bipyramidal is the geometry of this IF7 molecule. It is ideal and standard geometry of this molecule with bond angles of 72 and 90. Another example of hybridization is DsP2 hybridization. That is example is nickel Cn/4 2 minus complex. So central atom is nickel. Nickel ion exists in the +2 state. So electronic configuration will be 3d8. So in this molecule, 1 3d, 1 4s, 2 4p empty orbitals mix and form DsP2 hybridization. 4 DsP2 hybrid orbitals lie in one plane at 90 degrees centigrade, that is square planar geometry. So cyanide ligands act as a strong field ligand which causes pairing in the 3d orbitals. So 4 DsP2 hybrid orbitals accept lone pairs from the 4 cyanide ligands. That bonds are formed are called as coordinate covalent bond. Cyanide minus behaves as sigma donor and pi acceptor, that is called back bonding. So electronic configuration of nickel atom is 3d8 4s2, but Ni2 plus ion is 3d8. So in this 3d8 configuration, these are in the 2 unpaired electrons in observed in the d orbital, but this is a cyanide ligand is a strong field ligand, and when cyanide ligand comes in contact with this nickel ions, these electrons get pair up and make a vacant d orbital for hybridization. So this 1 3d orbital, 1 4s orbital, and 2 4p orbitals. So these 4 hybrid orbitals which are vacant. So this hybrid orbital accept the electrons from the ligand, that is cyanide ion, and therefore these are the electrons from these 4 cyanide ions, and so the hybridization is DsP2. So these 4 hybrid orbitals directed towards the 4 square corner of the square planar tetra corner, and therefore they are 90 degree from one another. So in this way this complex is formed, that is nickel Cn/4 2 minus complex having DsP2 hybridization, and the geometry is square planar. Then we will see the summary of this table having different hybridization and different shapes. So we will see one by one. So BF2 molecule hybridization is sp, bond pairs involved 2, lone pair 0. So expected geometry is linear and the observed shape is also linear. Another example is BF3 having sp2 hybridization, 2 bond pairs are involved. 3 bond pairs are involved. So hybridization is sp2, and their expected geometry is trigonal planar, and actual geometry also trigonal planar because there is no lone pair of electrons. In case of CH4 methane molecule, sp3 undergoes sp3 hybridization in which 4 orbitals are involved. These 4 bond pairs are involved with no lone pair of electrons. Expected geometry is tetrahedral and actual also tetrahedral. Another example is PF5 molecules which undergoes sp3d hybridization having 5 hybrid orbitals. So 5 bond pairs are involved with no lone pair So expected geometry is trigonal bipyramidal, and the actual also trigonal bipyramidal. SF6 molecule having hybridization sp3d2, that is 6 hybrid orbitals are involved, therefore 6 bond pair of electrons are involved, no lone pair. So expected and actual geometry are octahedral. In case of IF7 molecule, sp3d3 hybridization is involved, means there are 7 bond pair of electrons are involved. So the expected and actual geometry are same, that is pentagonal bipyramidal. Then SnCl2 molecule, which involves sp2 hybridization, but here in this case 2 bond pairs are involved and 1 lone pair involved. So expected geometry is trigonal planar, but actual geometry of this molecule is angular or V shape. In case of ammonia, sp3 hybridization is involved with 3 bond pairs and 1 lone pair. The expected geometry is tetrahedral, but the actual shape is pyramidal. In case of H2O molecule, sp3 hybridization with 2 bond pairs and 2 lone pairs. Expected geometry tetrahedral, but actually it is angular or V shape. SF4 molecule, sp3d hybridization with 5 hybrid orbitals, 4 are act as bond pairs and 1 as a lone pair. So expected geometry is trigonal bipyramidal, but actually it is a seesaw structure. Then another molecule is ClF3 having hybridization sp3d with 3 bond pairs and 2 lone pairs of electron. Expected geometry is trigonal bipyramidal, but actually it is bent T shape. Xenon-F2 molecule hybridization is sp3d with 2 bond pairs and 3 lone pairs, but expected geometry is trigonal bipyramidal, but the actual shape of the molecule is linear, with 3 lone pairs occupy on the equatorial and the 2 fluorine atoms, that is bond pair of electron, occupy at the axial position, therefore molecule is linear. In case of Xenon-F4 molecule, hybridization is sp3d2, means 6 hybrid orbitals are involved. Out of these 6, 4 act as a bond pair of electrons and 2 as a lone pair of electron. So expected geometry is octahedral, but the actual geometry of this molecule is square planar, because this lone pair act as a they are at axial positions, and the 4 bond pairs they are lie on the square planar corner of the square plane. Another molecule is IF5 molecule having sp3d2 hybridization. It involves 5 bond pairs and 1 lone pair. So it is expected geometry is octahedral, but the actual shape of this molecule is square pyramidal. So this is all about the hybridization concept.